Welcome to the 8th session of this integration series. In this session, we will illustrate integrals with exponential and logarithmic functions. We will use the average value of a function on an integral to solve questions with the polynomial integrand. We will also demonstrate the technique of integration by parts and their related examples. The aim is to reduce the degree of the polynomial. We will solve 7 worked examples in this session.
Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything.
Welcome to the 8th session of this integration series. Here, example 1 is to find a general solution of the integral of e to the 3x plus e to the x, or over the result of e to the 3x minus e to the x plus 1 with respect to x. Since the integrand can be simplified by multiplying e to the negative 2x on both numerator and denominator, it is then written to e to the x plus e to the negative x, or over the result of e to the 2x minus 1 plus e to the negative 2x, which equals e to the x plus e to the negative x, or over the sum of e to the x minus e to the negative x, or in parentheses squared plus 1. Since the differentiation of e to the x minus e to the negative x equals e to the x plus e to the negative x, the antiderivative can be written to the integral of 1 over the sum of e to the x minus e to the negative x, or in parentheses squared plus 1, d e to the x minus e to the negative x, or in parentheses by dx, which is written to the integral of 1 over the sum of e to the x minus e to the negative x, or in parentheses squared plus 1 with respect to e to the x minus e to the negative x, which equals arctangent of e to the x minus e to the negative x, or in parentheses plus c. Example 2 is to find a general solution of the integral of 1 over the product of 2 to the x and 1 plus 4 to the x, or in parentheses dx. As usual, we start to let u equals 2 to the x, which gives du equals ln of 2 times 2 to the x dx, and dx equals 1 over the product of u and ln of 2 du. Hence, the antiderivative is written to 1 over the product of u and 1 plus u squared, or in parentheses times du over the product of u and ln of 2, which equals 1 over ln of 2 times the integral of 1 over u squared minus 1 over the sum of 1 plus u squared, or in parentheses du, which equals negative 1 over the product of 2 to the x and ln of 2 minus arctangent of 2 to the x over ln of 2 plus c, after being simplified. Now, we herewith briefly introduce the definition of the average value of a function on an closed interval. Given that f is integrable on the closed interval from a to b, then the average value of f on the interval is the value of the definite integration over the length of the interval, and this concept will be used in our next example. According to the definition, if f of c is the average value of a function f of x over the closed interval from a to b, the mean value is expressed to the integral from a to b of f of x with respect to x over the result of b minus a, where c is inside the closed interval from a to b. Alternatively, the integral from a to b of f of x dx equals b minus a, or in parentheses multiplies f of c. Now it's time to look at some examples related to the average value problem. In example 3, the given criteria are that a0, a1, a2 up to an are all real numbers that satisfy the equation of a0 over 1 plus a1 over 2 plus a2 over 3 all the way up to an over n plus 1 equals 0. What does the question ask is to prove that the equation a0 plus a1x plus a2x squared all the way up to an x to the n equals 0 has at least one real 0. We start to let f of x equals the polynomial a0 plus a1x plus a2x squared plus all the way up to an x to the n according to the definition of the average value of a function over a closed interval. The integral from 0 to 1 of f of x dx equals f of c times 1 minus 0, or in parentheses, which equals f of c, where c is the value in the closed interval from 0 to 1, and f of c is the function average value over the closed interval from 0 to 1. Hence, the integral from 0 to 1 of the polynomial function a0 plus a1x plus a2x squared plus all the way up to plus an x to the n dx equals a0x plus a1x squared over 2 plus a2x cubed over 3 plus all the way up to an x to the n plus 1 over n plus 1, valued from 0 to 1, which equals a0 plus a1 over 2 plus a2 over 3 all the way up to an over n plus 1, which equals f of c, which equals 0. Since c is in the closed interval from 0 to 1, the polynomial function f of x has at least one real 0. That's complete our proof. Example 4 is to use the average value theorem to prove the inequalities of 1 over y is less than ln of y minus ln of x, or over the result of y minus x, which is less than 1 over x, given that x is greater than 0 but less than y. To prove these two inequalities, we need to construct functions such as x over y and y over x respectively. As for the first part of the inequalities, 1 over y is less than ln of y minus ln of x, or over y minus x. We let p equals x over y. Since x is greater than 0 but less than y, p is greater than 0 but less than 1. Now we introduce another variable t, which is defined in the open interval between p and 1. So 1 over t is greater than 1. Hence, the integral from p to 1 of dt is less than the integral from p to 1 of 1 over t dt. After executing the anti-differentiation on both sides of the inequality, we have the inequality 1 minus p is less than negative ln of p. That gives 1 minus x over y is less than ln of y minus ln of x. Further simplification can be done, and it is seen here that we finally have the inequality of what we want, that is 1 over y is less than ln of y minus ln of x, or over y minus x. Now we are going to prove the second part of the inequalities. In the similar manner, we start to assume a variable q equals y over x. Since y is greater than x and x is greater than 0, q is greater than 1. At the same time, we bring in another variable t, which is in the open interval from 1 to q. Since 1 over t is less than 1, we execute the definite integration from 1 to q on both sides of the inequality. Hence, the integral from 1 to q of dt is less than the integral from 1 to q of 1 over t dt, which gives q minus 1 is greater than ln of q. After substituting y over x for q, we have the inequality of y over x minus 1 is greater than ln of y minus ln of x. After being further simplified, the inequality relation of 1 over x is greater than ln of y minus ln of x all over y minus x. Hence, in summary, we have proved the inequalities 1 over y is less than ln of y minus ln of x all over the result of y minus x, which is less than 1 over x. Now we are going to introduce an important technique of integration, which is called integration by parts. Integration by parts is used to integrate the product of two or more functions. In the integration by parts, the formula is split into two parts, and for simplicity, these functions are often represented as u and v respectively. If both u and v are differentiable functions and based on differentiation product rule, we have the differentiation of product of u and v equals the differentiation of u multiplies v plus u multiplies the differentiation of v. Then we do the reverse operation, anti-differentiation, on both sides of the equation, and we have the integral of u dv by dx equals the product of u and v minus the integral of v du by dx. Now let's look at some examples how we use this integration by parts technique to find antiderivatives. Example 5 is to find two antiderivatives, and we are going to use this new technique, integration by parts, to find general solutions for these antiderivatives. As for the first antiderivative, first we let u equals ln of x and dv equals x dx. That gives us du equals 1 over x dx and v equals x squared over 2. Hence, the antiderivative is written to 1 over 2 times x squared ln of x minus the integral of 1 over 2 times x squared times 1 over x dx, which equals x squared ln of x over 2 minus x squared over 4 plus c. Here we continue to work on the second antiderivative of example 5. We start to let u equals sine x and dv equals e to the x dx. That gives du equals cos x dx and v equals e to the x. Hence, the antiderivative is written to e to the x sine x minus the integral of e to the x cos x dx. Now we apply the technique of integration by parts again on the integral of e to the x cos x dx, and assuming s equals cos x and dt equals e to the x dx, that lead to ds equals negative sine x dx and t equals e to the x. Hence, the integral of e to the x cos x dx equals e to the x cos x plus the integral of e to the x sine x dx. After combining the equations of 1 and 2, we have the integral of e to the x sine x dx equals e to the x sine x minus open bracket e to the x cos x plus the integral of e to the x sine x dx close bracket. After rearranging and simplifying the equation, the antiderivative equals e to the x over 2 multiplies sine x minus cos x, or in parentheses plus c. Example 6 is to find the two antiderivatives. As for the first one, the antiderivative is written to 1 over 2 of the integral of x squared e to the x squared with respect to x squared. Now we let t equals x squared, which gives dt equals dx squared. Hence 1 over 2 of the integral of x squared e to the x squared dx squared can be written to 1 over 2 of the integral of t e to the t dt. Now we apply the integration by parts technique to find general solution of this antiderivative. We let u equals t and dv equals e to the t dt. That lead to du equals dt and v equals e to the t. Hence the antiderivative is written to 1 over 2 times open brackets t e to the t minus the integral of e to the t dt close bracket, which equals t e to the t over 2 minus e to the t over 2 plus c. After substituting t for x squared, the antiderivative equals 1 over 2 times e to the x squared times x squared minus 1, or in parentheses plus c. As for the second antiderivative, since it is written to the integral of x ln of x over the product of x and 1 plus ln of x, or in parentheses squared dx, then we let u equals x ln of x and dv equals 1 over product of x and 1 plus ln of x, or in parentheses squared dx. That give du equals ln of x plus 1, or in parentheses dx, and v equals negative 1 over the sum of 1 and ln of x. Here we continue to work on the second antiderivative of example 6. In the previous slide, we have du equals ln of x plus 1, or in parentheses dx, and v equals negative 1 over the sum of 1 and ln of x. The antiderivative can be written to negative x ln of x over the sum of 1 and ln of x plus the integral of 1 plus ln of x, or over the sum of 1 and ln of x dx, which can be simplified to x over the sum of 1 and ln of x plus c. However, we are going to demonstrate an alternative approach for the second antiderivative here. Since the differentiation of x over the sum of 1 and ln of x equals ln of x over 1 plus ln of x, or in parentheses squared after being simplified, the antiderivative can be written to the integral of d dx of x over the sum of 1 and ln of x dx, which equals x over the sum of 1 plus ln of x plus c. Example 7 is to find two antiderivatives using the technique of integration by parts. As for the first one, we let u equals ln of x and dv equals x squared dx. That lead to du equals 1 over x dx and v equals x cubed over 3. Hence, the antiderivative is written to x cubed ln of x over 3 minus 1/3 times the integral of x cubed times 1 over x dx, which equals x cubed ln of x over 3 minus x cubed over 9 plus c. As for the second antiderivative, we let u equals cos x and dv equals e to the x dx. That lead to du equals negative sine x dx and v equals e to the x. Hence, the integral of e to the x cos x dx is written to e to the x cos x plus the integral of e to the x sine x dx. Then we use the same technique integration by parts again to rearrange the integral of e to the x sine x dx, which equals e to the x sine x minus the integral of e to the x cos x dx. Hence, the integral of e to the x cos x dx equals e to the x cos x plus e to the x sine x minus the integral of e to the x cos x dx. After being rearranged, the integral of e to the x cos x dx equals e to the x over 2 times cos x plus sine x, or in parentheses plus c. So the definite integral from 0 to pi over 2 of e to the x cos x dx equals e to the x over 2 times cos x plus sine x, or in parentheses valued from 0 to pi over 2, which is e to the pi over 2 minus 1, or over 2. If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.